This little video clip really is just a revision of stuff from the AS course on electric fields. So this particular topic is split in two halves. Part of it's done in AS, the rest is done in A2. You do not need to make notes on this unless you feel the need to do so. So the most basic thing about like charges, repelling and attracting is the first thing we can say. Electric field strength, force per unit charge, but the extra thing you have to have in there, this is this positive charge, force per unit positive charge. Gravitational fields, just simply force per unit mass, but because in the case of electric charge, we've got both positive and negative charges, then we need to be specific about direction, and that's taken into account by saying force per unit positive charge. So we have our definition, F equals EQ, from which we get, E equals F over Q, from which we get F equals EQ, newtons per coulomb. Representation of electric fields, basically, the direction of the arrows away from a positive charge and towards a negative charge. Fundamental, that's taken into account in the definition force per unit positive charge. So radial field lines there. In the case of a positive and a negative charge is what we call a dipole. Something like this. So if we had a positive test charge and we placed it there, it would experience a force in that direction. If we placed a positive charge there, it would experience a force in that direction, etc. If we placed a positive charge there, it would experience a force in that direction. Okay, we're just going to need to flip up the page a little bit here for the other diagram. This diagram I don't think is particularly good there. I would not expect those two field lines to be parallel. I'd expect the lines to be coming around like that a bit more. Okay, so just to be aware of that. That would be for equal magnitude charges in that the axis of symmetry here is down the middle. If one charge was larger than the other, then the diagram would be skewed one way or the other. All right, let's go back to full size. I think it's just a bit nicer to look at. Okay, uniform field. We do have this thing called end effect. You tend to get a gathering of charge at sharp edges, and because of that, you do get this curvature of the field at the ends. Just to be aware of that, generally speaking, I would not actually draw that in a diagram. And so you've got equally spaced parallel field lines representing that uniform field. The relationship between potential and electric field strength. Formula from last year, you might have known it as E equals V over D. But basically, if you put a potential difference across these plates and you know the separation of the plates X, then the electric field strength is given by that formula V over X. And the units are going to be volts per meter, which are going to be equivalent to newtons per coulomb. And the last thing, and we'll be coming back to this in our, I think it's in the third section of this topic for A2, electric potential, W divided by Q. Work done per unit charge. We're going to define it a little bit more fully than that, but at this stage, W over Q measured in volts, which are the same as a joule per coulomb.